All right, hey guys, so we're gonna start the review. I will warn you, this is going to be a very long review. We're gonna cover pretty much like all the important information from lessons 1 through 6. If you have any questions, feel free to stop me and ask. You can just put them right in the chat. Um, yeah, no, really, I just say get comfy. This is gonna be a very, very fun time. So going all the way back, starting with lesson 1, going back to the simplest of terms that you just gotta know, you've got the case, which is the experimental unit from which data are collected, and then you've also got the variables. It's the characteristic that's being measured. So basically, it's something that varies that we're interested in. So, for an example, teacher wants to know if Stat 200 students who spend more time studying get better quiz scores. So in this, the Stat 200 students would be the cases, and the quiz scores are the variables. Um, yeah, pretty much lesson 1 is just all, you know, terms, which isn't fun, but you gotta know them to understand the important stuff later on. So next up, we have categorical versus quantitative variables. So categorical, it's names that either can or can't have logical order. If it's nominal, then basically there's just no order. It's just put in whatever order someone decides. An example of this would be ice cream flavors. It could be in any random flavor you want. You could have vanilla, chocolate, mint chocolate chips, strawberry, pistachio, the new stuff that they have over at the creamery, some of that nice mint nittany or anything like that. It's all just arbitrary. Or you could have ordinal, where it does kind of have like a logical order, but it's not numbered. Think of like t-shirt sizes. You've got small, medium, large, or if you want to, you could go like extra small, extra large, all the way up to like quadruple X or something like that. So it just like it has an order, but there's no numerical value to it, but we just know it has an order. Um, then you've also got quantitative variables, which are numerical values that are placed in some kind of meaningful order, generally like smallest to largest. So you've got discrete, which is a set value. It's basically just kind of like, I guess, trying to think of a really good. Oh, you know what? We'll go with amount of rocks someone has. Someone either has like 10, 12, 15. They can't have half a rock. I'm making this up arbitrary because rocks. Or continuous, where there's like a value between values, where you could like go out to the millionth bajillionth decimal point. An example of this could be, like height, weight. If like you're measuring water, it could be in like, microliters, all. It's just basically like you can just derive it out many more places to like get a more accurate number. All right, explanatory and response variables. Explanatory variable, also known as the independent variable for, it might get flip-flop between what it's called on the exam or something like that. Basically, it explains the variation that occurs during an experiment. So it's the thing that you're manipulating in order to see what the result of the experiment will be. And with that case, the response variable or the dependent variable is basically the outcome of whatever gets manipulated. So let's say if you're like manipulating water levels in plants, then the explanatory variable would be how much water you get the plant, and the response would be like how much the plant grows or if it dies or not or something like that. All right, so population parameter versus sample statistic. There was a little bit of confusion about that, so I just like put this little thing in here quickly. So population parameter is used when talking about the population as a whole, and you only really use the sample statistic when you're talking about a statistic that's like calculated in the sample. I hope that makes a little bit more sense. And I guess like the two most important ones you should probably know are mean. It has the population parameter mu and the sample statistic of x bar. And you also have the proportion with a population parameter of p and the sample statistic of p hat. All right, so random sampling, method of obtaining, allowed one page for the exam, right? Whatever is said in the email, I think you're allowed like a note card that you can write everything on. All right, so simple random sampling, method of obtaining a sample from a population. That's completely random. Basically, think of it as like you've just got a bunch of, think of it like the lottery, where you just have a bunch of balls with a bunch of numbers on them. And all of a sudden, you just get like, uh, a few of them just randomly come out, then that is like your population. You could also like think of it where, you're just going along and you're like, just put it into like a random number generator and just getting out like names or something like that. It's all up to chance about who gets picked and who does not. So it's supposed to be completely accurate of the population. And it's also selected without replacement. So you're not going back and like once you get someone, you're not putting them back in to then potentially get them again. But then you also have something called convenience sampling, where it's basically they're doing what's the most convenient for the researchers. So, it's just the easiest to do. It's not random, and so you won't get like a completely representative population. So you can't really trust any of the information that comes out of that sample, which leads us into biases. So I know back in like we were going over biases, non-response and response bias had a lot of confusion. So I'm hoping it's kind of like understood a little bit better now, but going over it anyway. So the non-response bias, it's basically when individuals can choose to participate in the study, research, whatever's going on. And so generally what happens is those who do participate feel very differently than the average population. They generally feel like much stronger about something. So think about like when you're completing a survey or a review or something like that for say a restaurant or like a product on Amazon, you're more likely to leave like either a 5-star or a 1-star review saying like, oh, this is the most amazing thing I've ever had in my life, or oh, this is awful, no one should ever like do this, than you are to ever see like a 3-star review where it's just like it was all right. you know that's just the way it is because most people don't see the point in completing the surveys and giving feedback. um, then you also have response bias where the participants are not truthful about their answers, and it can be done for a number of reasons, but basically it's basically just kind of like, let's say in this example, it's when you're doing an exam, you're saying you studied a lot more than you actually studied for the exam. It's like a PISA teacher, because teachers always like to see like, oh, this person studied 300 hours for my exam, amazing, rather than see someone who said they didn't study, uh, just something like that. But then there's also kind of like, if they want to align more with like what the society wants, then it'll be like, oh yes, I don't do drugs or I don't drink alcohol, that's not illegal, something like that, where they just lie for the purpose of like making it, because that's what they think they want, like the researcher wants to do. So yeah, those are the two main biases that you can kind of get. um, so you also have the types of studies. So you have experimental. That's basically where something is being manipulated. It is also called a scientific study. You might hear it in two different ways. And that's it's going to be the one that's probably going to appear most on your test, is just, like one variable is being manipulated to see the effects that happen. Observational, basically, you're just going out, looking in the real world and just collecting data. You're not manipulating anything, but because of that, you can also get, like confounding variables, which have a number of names, third variables, lurking variables, stuff like that, that basically, it's related to both the explanatory and the response variable, and it just messes up your outcome. So an example of this is an increase of ice cream and an increase of shark attacks. So a researcher might think, oh, eating ice cream leads someone to get attacked more by sharks, which is preposterous. It's basically just saying that, you know, as it gets warmer, then, yeah, this video is going to be on YouTube. I will upload it after we're done with this. So you'll be able to rewatch it and anything else you want to do after. So basically, it's just kind of like, you know, if you're assuming that because more people are eating ice cream, they're getting attacked by more sharks, you're wrong. Most likely, it's just a confounding variable of because it's hotter, more people are buying ice cream and more people are being out in the water where sharks are. So you always have to be careful of those like confounding variables. All right, so you got types of groups. You've got the independent groups where its stuff is completely unrelated. So it's just kind of like, so you're studying the amount of coffee that someone drinks and what gender they are. That, you know, it's not really related in any way, shape, or form. You're not like studying the relationship between that. You're just trying to see like how much coffee people drink. Then you have like paired groups where they are matched in some way, and this can also be called match pairs. That's how it was presented a lot in when I took the class. So an example of this is kind of like your exam scores for your midterm and your final. Basically, like you can kind of predict how you're going to do on the final based on how you did for the midterm. That's just, you know, kind of how it goes. All right. So blinding. This is kind of a way to avoid bias. So you have single blind, where one side is generally the participants do not know what treatment they're getting, but the other side knows. In this case, they're getting a placebo, where I say, you know, a placebo is something that appears like an active treatment, but actually does not contain an active treatment. So think of like a sugar pill when they're doing like some kind of medical research where they give people, they give a placebo of a sugar pill, but they give people an actual pill that has treatment in it. You've also got a double blind experiment where neither the participants nor the researchers know which treatment has been assigned. This is another way to just kind of like avoid bias because, you know, bias is everywhere. And then in a lot of cases, you also have a control group where they don't receive the actual treatment. They get placebo or nothing. They're just trying to see like the baseline effects versus, you know, what the other experiments are getting. All right, so with that, we're already into our review one. If you've been watching my videos before, you know this is a little weird. Normally we do the reviews at the end, but I thought it would be best if we did the reviews like scattered throughout the exam, trying to retain, scattered throughout the review to retain interest and just also like relate to what we've been talking about. So question number one, a teacher wants to take students' IQ scores and use them to predict end of semester grades. So the researcher or teacher takes a sample of 1,000 students, records their IQ score and their semester grades for each of the individuals. And in this scenario, what is the explanatory variable? Is it the semester grades? Is it the relationship between IQ scores and semester grades? Is it the 1,000 students or is it the IQ scores? All right, so I'll give you guys a little bit of time to answer this. You can just type in the chat. All right, so it looks like you guys are getting it. Yep. In this scenario, the IQ scores are the explanatory variable, in which case the semester grades would then be the response variable. There you go. Congratulations. Next up, so which of the following is not a quantitative variable? Is it height, battery percentage, exam score, or t-shirt? I'll give you guys another little bit of time to answer. in hindsight, I will say I probably should have made the answer a little bit different than the one from the first one. But congratulations to everyone who said T. Yep, you guys know what you're talking about. T-shirt size is, unless specifically like told, they're like giving you like a certain number size. It's just going to be like small, medium, large, stuff like that. So, which in that case is a categorical variable. All right. So moving on, we have one categorical variable. Basically, use a proportion to summarize data concerning one categorical variable, where a proportion equals the number in the category divided by the total number. Population parameter, you just have big P, sample proportion, you have P hat. And your proportion has to be between 0 and 1. So, all that fun stuff. We've also got risk, which is kind of an offshoot of proportion. It's a probability that an event will occur. It's calculated like almost the exact same way, where it's just the number with the outcome divided by the total number of outcomes. So an example I just kind of like thought up was the flu. So I gave random numbers. So 103 out of 1,000 children get the flu each year. So then the risk would be there was 103 that get it over the total number of children. And so you get 0.103 or about 10%. So about 10% of children get the flu each year. That's kind of like the risk. The odds is comparing the likelihood of an event happening with the likelihood the event is not going to happen. It has two formulas. So you can go with odds equals number with the outcome divided by the number without the outcome. Or if you've already calculated the risk, then you can use this equation. If you haven't, then I don't really think it's worth it to find the risk and then do this, but whatever floats your boat. It's odds equals the risk divided by 1 minus the risk. So if we're continuing with the example that I did in the last slide, odds equals 0.103 divided by 1 minus 0.103, or in this case, it'd be 0.103 divided by 0.897, which is equal to 0.115. So the odds of a child getting the flu is 0.115 to 1. I hope that, makes some sense. So then here are some visual representations of one categorical variable. So I hope you guys appreciate, the little, I made a funny that since it's a pie chart, it's about desserts. Sorry, I'm really tired. So you have frequency table, which is this top bit here, which basically it just breaks down the, two different things, two different, like, where it's, this is two-way. Regardless, this is a two-way frequency table. I'm sorry, people, but it's basically just like, do you like muffins? Like, what's your favorite dessert? Is it muffins, cookies, brownies, or cupcakes? Disregard gender. That's annoying. But then, you got the pie chart here where it has, it's just kind of like sequestered off into sections of the circle as to, what percentage responded with that given response. And then you've also got bar chart, which is over here, where it's just, like what kind of pets you have and who said they had them. So, and then you've also got two categorical variables. I apologize, this is a little cut off. There's this formatting issue. So it's basically breaking down on the left side here, it's got gender. And then on the top, it's got 3 different sports, whereas football, basketball, baseball, and then it has a total. And so you basically just have 2 different variables where it's what's your gender and what's your favorite sport. All right, so probability. It's basically the probability that an event will occur. To calculate its number in the group divided by total number. It has to be between 0 and 1. If it's 1, then it's basically guaranteed to happen. So an example of this is like getting a number between 1 and 6 on a 6-sided die. You got to get something between 1 and 6, unless the die like explodes or something. I digress. And if you get a 0, then it's impossible for the event to happen. So an example of this would be like rolling a 7 on a 6-sided die. It's just not possible. All right, so disjointed and independent events, they're different. It's disjointed basically means that there are events that can never happen at the same time. An example of this that I like to use is like class standing. Someone can't be both a freshman and a sophomore at the same time. They can be a freshman and then a sophomore and then a junior and senior, but they can't be one at the same time. Meanwhile, independent events, they're just completely unrelated. One does not affect the outcome of another. So I just quickly like put down here, like the amount of birds in a city have any effect on traffic. It really doesn't. I mean, it might affect how many birds poop on your car, but that's all that's going to affect. It's not going to, they don't affect each other. All right, so combination of events. I also just noted here for union that I'll get to. So you've got intersection, which is basically just the probability of A and B. You've got union, that's the probability of A or B. And you should note that this includes the possibility of A and B. And so I know a lot of you were confused when we were going over this way back when. But basically, like, the equation's so weird because you have to subtract the possibility of A and B because it's basically counted in there twice. So that's why the equation's really weird. We've also got complement, which is the probability of not A, or the conditional, which is the probability of A given B. And outliers, everyone's favorite. So they're simply just observations that fall outside like the general scope of what the other observations are. As you can see here, the one that's way up here when everything else is much down here, that's considered an outlier. And you can see them in pretty much every single graph form. They're just something to always be aware of because they do affect the distribution. They affect all the values they get out of it. They can affect pretty much everything. So just always remember your outliers. All right, so going into shape. So a symmetrical distribution, it's the same. A subset of that is the normal distribution that we'll be talking a lot more later. It's the mean equals 0, standard deviation equals 1. It's the bell shape that a lot of stuff is based off of. Fun times. And skewness. So it's basically considered skewed if the values are more spread out to one side of the distribution than the other. You can tell skewness by following the tail. So in this case, you can see the tail goes off this way. It's a left skewed, and right skewed one, the tail's over on the right and kind of like skews up. Like these graphs, they pretty much demonstrate what I'm about to talk about, like right after this. So measure of central tendency. The mean, it's the average calculated by a sum of all the data points. You got the median, which is the exact middle of the distribution ordered from smallest to largest, and the mode, which is the most frequently occurring value in the distribution. Not really much to say about those, but then it's the skewness, how it affects mean, median, mode. So if it's symmetrical, then the mean equals the median, which equals the mode. If it's right skewed, then the mode is less than the median, which is less than the mean. And if it's left skewed, then the mean is less than the median, which is less than the mode, which makes sense when you graphs because you can see that you've got all these data points over here that's just dragging the mean down, and so it's making the mean much lower. Meanwhile, the mode is also going to be much higher because you've got more frequently occurring values over on the right side, but the left side is just messing that up. And it's like the exact opposite for the right skewed. All right, so empirical rule, everyone's favorite. You guys probably have also heard it referred to as the 95% rule. It basically says that 95% of all observations are going to fall between 2 standard deviations of the mean on normal distribution. Really fun, I know. So on a normal distribution, about 68% of the data is going to fall within 1 standard deviation, 95 will fall within 2 standard deviations, and 99.7 will fall between 3 standard deviations of the mean. And that brings us to everyone's next favorite stuff, z-scores. So it's basically used to describe one observation in relation to the rest of the distribution. And so z-score equals x minus x bar divided by s, where s is the original data value. So generally it's going to be the one that they give you. X bar is the mean of the original distribution, and then the s is the standard deviation. So review 3, this is my dog. She is very cute. And so she is a Portuguese water dog. So the average weight of Portuguese water dog is about 55 pounds with a standard deviation of 5. So what is the z-score for a female Portuguese water dog that weighs about 62 pounds? Give you guys a little bit of time to answer this, and also just admire how adorable she is. I really miss her if you can't tell. All right, yeah, you guys seem to be getting it. It is, in fact, B. So basically, just to calculate this, you take the 62, that is the weight of the given weight. You minus that by the average, which is 55, and you just divide it by the standard deviation of 5 to end up getting 1.4. All right, next up, we've got percentiles. So basically what a percentile is saying is it's a portion of a distribution that's less than a given value. So very common example is test scores. So if a student scores in the 51st percentile, then they scored better than 51% of the other students that took the test. I know like 51% seems a little weird, but I just always use it because one of my teachers always bragged that he was in like the 51st percentile in the SAT and that he was so happy he was above average. I always thought it was funny. Super qualified. All right. So we also have a 5-number summary. This is one of the most important tools for just like deciphering box plots and other stuff. So it basically goes with a minimum, a Q1, a medium, a Q3, and a maximum. The Q1 is the first quartile, also known as the 25th percentile, and Q3 is the third quartile, better known as the 75th percentile. And then most of the stuff you'd ever be asked to calculate with it is range, which is just simply the difference between the maximum and the minimum. So it's basically just range equals max minus min, and IQR, which is Q3 minus Q1. So going to that, we already have our next review. So teacher wants to examine test scores from the most recent exam. The 5-number summary goes as such: 46, 63, 70, 77, 85. According to the 5-number summary, what is the IQR? I'll give you guys a little bit of time to figure this one out. All right, yeah, you guys got it. You guys got it. It's simply just because it's asking for the IQR, you take Q3, which is 77, minus Q1, which is 63, and you end up getting 14. Way to be, guys. Way to be. All right, so this is a single box plot. This is what it looks like. I don't know why it got cut off, curse formatting, but basically what should be down here is you've got the minimum down here that's attached to a nice little tail. And as soon as you touch the box, you've got the Q1. The red line here is the median. Followed after that, you've got the upper quartile at where the box ends. And then all the way up here is the max. And you've got all these outliers out here that you can just disregard because, they're outliers. So identifying outliers with the IQR method, this basically just comes in with like any box and whisker plots. Sometimes you get with, some other like just when they give you amounts of data, but Yeah. So basically, to do it, you basically want to find the lower fence and the upper fence. So the lower fence is Q1 minus 1.5 times the IQR. The upper fence is Q3 plus 1.5 times the IQR. And so what's with the method, basically, if there's anything that's below the lower fence and anything above the upper fence, is basically considered an outlier. All right, scatter plots. So they're used to show a relationship between explanatory and response variables. Things to always consider when you're looking at them is what's the direction? Is it positive or negative? Is it going up or is it going down? The form, is it linear or nonlinear? Most of the time, it's if you see like a graph, it's going to be linear, but there are always some that look kind of weird. Strength, you've got weak, moderate, and strong. That's basically just the R value, which we'll be going into a little bit later. And are there any outliers? Because that can affect things. Outliers are known to do. So correlation, it's the measure of the direction, strength, or relationship between two variables. This is most commonly referred to as R. So it's going to be in between -1 and 1. If R is greater than 0, then there's a positive association. If it is less than 0, that's a negative association. The closer it is to 0, the weaker the relationship, but the closer it is to positive or -1, the stronger the relationship is. You don't have to worry about sign. That just says whether it's a positive or negative relationship. But when it comes to like what's the strongest relationship, the closer it is to 1, the better. It doesn't matter like the sign of if it's positive or negative. So correlation has no unit, and the correlation between x and y equals the correlation between y and x. Is basically just saying that no matter which way you spin it, it's always going to be the same. So quickly made a handy dandy little chart here. So if the R is between 0 and 0.2, then it's a very weak relationship. If it's between 0.2 to 0.4, then it's a weak relationship. If it's between 0.4 to 0.6, you got a moderate relationship. If it's between 0.6 to 0.8, then you have a strong relationship, and 0.8 to 1, you have a very strong relationship. Just, something to tuck away in the back of your mind when it comes to the exam. And then you've also got simple linear regression. So it's a straight line that is used to predict the response variable using the explanatory variable. It does not matter which one you select as y or x because it should, either way give you the answer. So the equation is y hat equals a plus bx, where y hat is the predicted value of y for a given value of x, a is the y-intercept, and b is the slope. If it looks familiar, there's a reason. It's pretty much like y equals mx plus b, just with a very little amount of substitution. So just a little bit of going back to algebra there. And then you've also got residuals that kind of come from using the simple linear regression, where it's the difference between an observed y value and a predicted y value. So the equation for that is E equals y minus y hat, where y is the actual value of y, and y hat is the predicted value of y. All right, so review 5. According to the box plot, that's right there, which of the following is approximately represented by a score of 505? Is it the Q1, median, minimum, or Q3? I'll give you guys a little bit of time to look at it. All right. I see some conflict. So most of you kind of fell into the little trap and you thought it was the minimum. But the minimum is way down here, which note is below 500. So it can't be approximately 505. is probably like 490 something. But up here, this is Q1, which is just a little bit above 500. So it is the closest to being a 505. So for those that I got, this is surprising. I think this is the first time I've ever done that. To those who got it, congratulations. And to those who didn't, I doubt you're ever going to see something that's like this nitpicky. But just remember that right here is the minimum. This is Q1. This is the median. This is Q3. And up here is the max. All right, so number 6, which of the following has the weakest association? Is it 0.01, negative 0.02, 0.99, or 0.53? All right, you got me. Yep, 0.11. Congratulations. All right, so confidence interval and sampling distribution. So confidence interval is a range computed using sample statistics to estimate an unknown population parameter given a stated level of confidence. The sampling distribution is the distribution of sample statistics with a mean approximately equal to the mean of the original distribution and a standard deviation known as standard error. So we're about to dive a little bit deeper into this. So confidence intervals. A confidence interval is equal to the sample statistic plus or minus the margin of error. You guys always have to be careful on your test or on homework or something because sometimes they might already give you the margin of error and you might multiply it because you think, oh, I've got to do the multiplier, like generally 2 times the standard error. But no, if they give you the margin of error, then you're set. So what the margin of error depends on is level of confidence that, I nicely just broke down this little chart here. It's based off the empirical rule where it's saying if it's 68%, confidence is 68%, then it's got to be 1 standard deviation from the mean, 95%, 2 standard deviations from the mean, and 99.7, 3 standard deviations from the mean. So if you understand the empirical rule, then you're set. And so, then it's also just whatever the confidence level is multiplied by the value of the standard error. And so for a 95% confidence interval, you get 2 times whatever standard error. So concluding confidence interval, something very, very important. So for your final answer, you're going to get like a range because it's plus or minus, the margin of error. And so you're going to want to like write this in a conclusion statement. So this is how it's always going to like appear in your exam or something is I am blank percent confident that the population, whatever it is between the lowest number and the highest number. I imagine you guys have dealt with that a lot, so not nearly as nice as when I was first introducing you to it. So next up, we got bootstrapping. It's a resampling procedure that uses data from one sample to generate another distribution. It can also be called like sampling with replacement. So some values they can appear more than once and some might not occur at all. But the thing that you always have to like realize is that you have to have the exact same sample size as the original sample. And the distribution of many bootstrap sample means is known as the bootstrap distribution. So basically what's going to happen is think of it as, when you're doing, like I'm going to go back with the lottery again. Think about West Lottery and they just pull out, one of those random balls that has a number in it. But instead of just like setting it down, they throw it right back into the machine and there's a chance of coming back out again. That's like basically the best way of looking at it. And so if you do that, then you might get, there's a chance you might get the same value every single time you do it. There's a chance you might get like it a few times, and then you get a bunch of other ones. It's completely random what you get. And that's, what's supposed to happen. And so I'd just say any questions you might see on the exam are definitely going to be ones to try and trip you up. So if it's something with bootstrapping, they might have something that's like a little bit less than the sample size or a little bit more than the sample size, in which case you can just cross those off right away. You might, it's basically if you can't get a value that wasn't in the original sample and you have to get the same sample size. So if one of those two scenarios are not met, then you can just cross the answer off immediately. You just gotta stick to your guns. All right. This is a really quick slide. So basically, impact of the sample size on the confidence interval is an inverse relationship. So as sample size increases, standard error decreases, or the opposite is also true. As standard error increases, then sample size decreases. All right. Hypothesis testing. So basically, you're trying to compute the probability that a population with specified parameter would produce a sample statistic that is like as extreme or more extreme than the one we observed. The probability is known as p-value, and it's used to estimate the significance. And so basically, if a sample statistic is very unlikely, then we have to conclude that the differences that were made were actually it can't be from a sampling error. It has to be that there's actually a difference in the population. Using MATAB, nope. You will not be using MATAB Express on the exam. You're not going to be allowed access to any outside sites, so you're not going to be using MATAB, you're not going to be using StatKey or anything else like that. You're going to be using just the exam. So hypothesis writing, each test has a null hypothesis, HO, and they should give you, you should I'd definitely say write down whatever like formulas you might need. I don't think you're going to need too many actual formulas, but better safe than sorry. So each test has null hypothesis, HO, and alternative, HA. So the null hypothesis generally states there's no difference in the population, while the alternative states there is some kind of difference in the population. And so always four things that you should know when you're writing the hypotheses. Basically, you have to decide what is the parameter being tested. Is it the mean? Is it the proportion? Is it a difference in proportions? Stuff like that. What is the direction of the test? Is it is the sign a less than? Is it greater than? Or is it not equals to? That generally means if it's not equals to, then it's a two-tailed test. If it's less than, that's a left-tailed test. If it's greater than, that's a right-tailed test. And then you also have to know that what is the value of the hypothesis parameter. That's basically the number that goes into all the hypothesis statements. I know you guys have probably seen this a lot. And just one last thing, it should always be written in terms of population parameters. All right, so randomization procedures. Basically, you want to construct sampling distribution that can be used to make inferences about the population. It should be made assuming that the null hypothesis is true, so it's going to be centered around the null. You're going to then use that to find the p-value, and then based on the p-value, generally if it's less than 0.05, you're going to accept or reject it. So if it's less than 0.05, you reject. If it is greater than 0.05, then you fail to reject. Some key things: never accept the null hypothesis. Just not allowed to do that. If you do that, shame on you. Shame on your cow. You bring dishonor. And conclude in terms of the null hypothesis. And you want to also state it in a real world conclusion. All right, so review number 7, just asking a question. The majority of PSU students have a pet. So what is the correct null hypothesis for this question? I'll give you guys a second. All right. So most yep, it's p equals 0.05. That's the null. The alternative would be p is greater than 0.50. So good job. I know this question might have been a little bit confusing just because it's asking a question here that you'd immediately kind of like leap to go and look at the alternative, but really no. So review number 8. We construct a sampling distribution and get a p-value of 0.06. Based on that, what can we conclude? Yeah, you guys got it. You're going to fail to reject null hypothesis because the p-value is greater than 0.05. If any of you even thought about accepting the null hypothesis, bad. No, can't do it. Just can't do it. Oh, no. Well, I hope you guys like the answer. Sorry, guess there was an error here. Yeah, good job, guys. You got it. It's D. So just make sure you understand like what the question was getting at. So there's a question being asked: is the average weight of all PSU students different from 105 pounds? So then, what would we use in this scenario? Kind of like right off the bat, you can see it's asking for the average, so you can assume mean. So you can cross off proportion. You know, if it says proportion, you can just cross that off. And so confidence interval is really used to like make an estimate. So given that we already have some kind of value that we're estimating, we can't really use a confidence interval. Meanwhile, the hypothesis test, you know, it's giving us a value, it's asking is it different than this value? Besides the chart. Do you mean picking between confidence interval hypothesis testing or between like which parameter? Because parameters you just have to like look at what it's asking for. You know, it's asking, is it yeah, parameters. Basically you just have to like break it down into what it's asking for, whether it's, you know, like they're giving you generally if it says average, just immediately like leap on it, oh, it wants a mean. If it gives you a percentage, then you can kind of assume proportion, you know, stuff like that. I'd really say, you know, if it's you have to like just break it down to what kind of variable. If it's a quantitative variable, then it's going to be mean. If it's a categorical variable, it's going to be proportion. And if it asks for a difference, then you can kind of be like, oh, well, it's going to be either difference in mean or difference in proportion, stuff like that. So you just gotta like break it down to its lowest common denominator and then kind of build it back up. And that's how you can kind of like go between the parameters and everything. All right. So we are so close to the end, guys. So type 1 and type 2 errors. Basically, when you're conducting a hypothesis test, you only have 2 real decisions. You either reject a null or you fail to reject a null. Meanwhile, a hypothesis test is only used to make inferences, so we don't actually know if it's correct or not. So when we reject the null, there could actually be a difference in the population, in which case we're correct. Go us. Or there might not be a difference, but our sample was wrong, and so an error was made. Meanwhile, if we fail to reject the null, and so given that, you know, if the null hypothesis is true and there is actually no difference, then we made the correct decision again. Go us. But there could be a chance that there is a difference in the population, but it was not rejected, so an error was made. So here's the handy dandy little chart of trying to understand it. So basically you have here your decision of whether we reject the alternative hypothesis or fail to reject the alternative hypothesis. Sorry, null. Oh my God. So decision of whether to reject the null or fail to reject the null. And then in reality, if the null is true or if the null is false. So basically, if we reject the null, but the null is true, we made a type 1 error. If we reject the null is false, correct decision. If we fail to reject the null and the null is true, good job. If we fail to reject the null but the null is false, type 2 error. So following that, we got power, which is basically the probability of correctly rejecting a null hypothesis. That's all you need to know. You don't have to know how beta is calculated. They'll generally give you a beta, and beta is just the probability of committing a type 2 error. And so, given all that, it's just power equals 1 minus beta. Really simple, really straightforward. Just, you got it, guys. All right, we are so close. All right, so review number 10. Oh, God, I really don't want to read this. All right, so a group of teachers are comparing two different ways to how to teach a lesson. Either they're giving a pure lecture or they're having a group discussion. They want to know which students prefer. And so they get a sample and they're taught, using both ways and ask for which one they prefer. And then a statistical analysis performed to determine if more than 50% of, those that were, if the students, prefer. So the null is 0.5. The alternative is greater than 0.5. And so which of the following is true? This is a left-tailed test. There is a type 1 error present. Population proportion is being tested, or I am so tired and this review is boring, just end it already. I'll give you guys a little bit of time to decide on that one. Yeah, you guys got it. The correct answer is D. But no, in all reality, it is C, that the population proportion is being tested. And you can tell it right here because it's using P. Kind of dead giveaway. But all the other giveaways got the 50%, and it's just asking which students preferred given categorical variables. You can't really tell if a type 1 error is present, considering you haven't decided to reject or fail to reject a null yet, so impossible to decide. And it's also not a left-tailed test because it's the greater than sign, so it would be a right-tailed test. And I'm kind of with you guys on D. So, all right, I think this is the last one. So in the previous question, we determined that we should reject the null. We're just coming up with this on the spot. Suppose we reject the null, but the students actually do not prefer the group discussion over the lecture. So then which of the following is true? There's a type 1 error, there's a type 2 error, there's no error, or this is awful, I just want to see another picture of your dog. Yep, the correct answer is A, but don't worry. I don't have any more pictures of my dog in this review, but I will in future reviews. She actually had to go in for a surgery a little while ago, and so she had to wear these special pink goggles, and she looks so cute in them. Oh my God, my heart melts every time. I'd also start putting in some pictures of my girlfriend's dog because she's got this giant Dalmatian, and oh my God, he is so chubby. It's so funny. So with that, we're officially done. Thank you so much for listening and bearing through it. I wish you all the best of luck on your midterm. If you have any questions, let me know. If you want to see this one live again, I will be doing it again on Sunday at 9. But this exact one, yeah, this is the same review that's going to be going on when I do it on 9. October 7th. I will also be uploading this to YouTube so people can see it again. And yeah, hope everyone has a good night and